Buffer solution definition. If it is sometimes necessary that a solution of defined pH be prepared and stored, the preservation of such a solution is even more difficult than its preparation. If the solution come in contact with air, it will absorb carbon dioxide and become more acidic. If the solution is stored in a gas bottle, the alkyl impurity present in glass may dissolve into the solution and may alter its pH. A buffer solution is defined as the solution which resists any change in its pH value even when small amount of acid or base added to it. Type of buffer solution. Type of buffer solution. There are two type of buffer solution of single substance, the solution of salt of weak acid and weak base. Example, ammonium acetate CH3COONH3 act as a buffer. Solution of mixture. There are further of two type, acidic buffer, basic buffer. Acidic buffer, it is a solution of mixture of weak acid and a salt of this weak acid and strong base CH3COH plus CH3CONA or HCOOH or H plus HCOONA. Basic buffer, it is a solution of mixture of weak base O and a salt of weak base with a strong acid. Example, NH4OH plus NH4Cl or NH4OH plus NH4NO3. Buffer action. The property of a buffer solution to resist any change in its pH value even when small amount of acid or base added to it called buffer action. The buffer action is of different type may be explained as follow. Buffer action of ammonia acetate solution. Ammonium acetate, like all other salt, is almost completely dissociate in aqueous solution as follow. CH3COONH4 dissociate into CH3CO negative plus NH4 positive. Thus, in the solution there is excess of CH3CO negative ion and NH4 positive ion. When a few drops of an acid are added to the above solution, the H3O positive ion given by acid combined with the CH3CO negative ion to form weakly ionized molecule of CH3COOH. CH3CO negative plus H3O positive give CH3COOH plus H2O. Thus, the H3O positive ion concentration of the solution does not change practically, hence the pH of solution remains almost constant. Similarly, when a few drops of base are added to the above solution, the OH negative ion given by the base combined with NH4 positive ion to form weakly ionized molecule of NH4OH. NH4 positive plus OH negative give NH4OH. Thus, the OH negative ion concentration, hence the H3O positive ion concentration or the pH of solution remain constant. On the contrary, the solution of substance like NaCl can act as a buffer because NaCl dissociate completely to give Na positive and Cl negative ion. These may be combined with base or acid to form NaOH or Cl, but these ionize completely to give back the OH negative ion or H3O positive ion. Thus, the H3O positive ion concentration of the solution changes, hence the pH of the solution changes. Buffer action of acidic buffer. For example, let us consider the buffer action of acidic buffer containing CH3COOH and CH3CONA. Acetic acid dissociate to a small extent, whereas sodium acetate is almost completely dissociated in the aqueous solution as follows. CH3COOH plus H2O dissociate into CH3COO negative plus H3O positive. CH3COONA gives CH3COO negative plus Na positive. By common ion effect, the ionization of CH3COOH is further suppressed. Thus, in the solution there are excess of acetate ion and small amount of H3O positive ion. When a few drops of an acid are added to the above mixture solution, the H3O positive ion given by the acid combined with the HCH3CO negative ion to form weakly ionized molecule of CH3COOH. CH3COO negative plus H3O positive give CH3COOH plus H2O. Thus the H3O positive ion concentration, hence the pH of solution remain almost constant. Similarly, when a few drops of a base are added, the OH negative ion given by a base combined with the H3O positive ion already present to form weakly ionized molecule of H2O. H3O positive plus OH negative give 2H2O. As the H3O positive ion are consumed, the equilibrium shift toward right, and thus more of CH3COOH dissociate to make up the loss of H3O positive. Hence, the H3O positive ion concentration over the buffer of pH solution does not change. Buffer action of basic buffer. The buffer action of the basic buffer NH4OH plus NH4Cl may be explained as follows. NH4OH dissociate to a small extent, whereas NH4Cl dissociate completely in aqueous solution as follows. NH4OH dissociate into NH4 positive plus OH negative, whereas NH4Cl dissociate into NH4 positive plus Cl negative. By common ion effect, the ionization of NH4OH is further suppressed. Thus, in the solution, there are excess of NH4 positive ion and a small amount of OH negative ion. When a few drops of a base are added, the OH negative ion given by it immediate combined with NH4 positive ion to form weakly ionized NH4OH. NH4 positive plus OH negative give NH4OH. Thus, the H3O positive ion concentration over the pH of the solution remain unaffected. Similarly, when a small amount of an acid is added, the H3O positive ion given by it combined with OH negative ion already produced by NH4OH in equilibrium. H3O positive plus OH negative give H2H2O. As the OH negative ion are consumed, the equilibrium shift in forward direction. Thus, more of NH4OH dissociate to produce more of OH negative ion, which make up the loss of OH negative ions. Hence, the OH negative ion concentration and therefore the H3O positive ion concentration over the pH of the solution remain fairly constant. Retain in memory. The buffer as explained as the weak acid buffer and the weak base buffer. However, solution of strong acid like HCl, HNO3, etc. of suitable concentration also act as buffer with low pH, and the solution of strong bases like NaOH, KOH of suitable concentration also act as buffer with high pH. Explained below. Strong acid buffer. A strong acid is completely ionized in aqueous solution, hence H positive ion concentration is very high. The addition of small amount of an acid or base has negligible effect on the pH of the solution. For example, addition of 1 centimeter cube of 0.1 m HNO3 to 100 cc of 0.01 molar HCl changes its pH from 2 to 1.96, which is a negligible change. Strong base buffer. A strong base is completely ionized in the aqueous solution. Hence, OH negative ion concentration is very high. The addition of a small amount of acid or base has negligible effect on OH negative ion concentration, hence pH of H positive ion concentration over the pH. For example, addition of 1 centimeter cube of 0.1 m HCl to 100 centimeter cube of 0.01 molar NaOH solution changes its pH from 12 to 11.96, which is a negligible change. Calculation of pH of buffer mixture. For acidic buffer, Hendron-Henschlich equation. If the weak acid is Ha and its salt is Ba, then Ha plus H2O dissociate into H3O positive plus A negative. Ba is dissociate into B positive A negative. Ka is equal to concentration of H3O positive A negative divided by concentration of Ha, or H3O positive की concentration is equal to K concentration of Ha divided by concentration of A negative. But A negative concentration is equal to Ba. Therefore, H3O positive is equal to K into concentration of HT divided by concentration of Ba is equal to concentration of acid divided by concentration of the salt. pH is equal to minus log of H3O positive. तो is equal to minus log K acid की concentration divided by salt concentration is equal to minus log Ka minus log acid concentration by salt concentration, or pH is equal to pKa plus log salt concentration by acid, or substituting the value of H3O positive from equation 1 to equation 3, we get pH is equal to minus log K minus log Ha concentration by A negative concentration. So pH is equal to pKa plus log conjugate base divided by acid concentration. It is interesting to observe from equation that if the salt is equal to acid, pH is equal to pK. Further, salt divided by acid is equal to 10. pH is equal to pKa plus 1. If acid divided by salt is equal to 10, pH is equal to pKa minus 1. Thus, the ratio of conjugate acid-base pair is changed by 10 times. pH is equal to minus plus 1. For basic buffer mixture, BOH plus BA is a similar manner. POH is equal to PKB plus log salt by base. pH plus POH is equal to 14 can be calculated. Alternatively, the above equation in different form. pH plus POH is equal to 14. pKa plus PKB is equal to 14. For now, substituting this value in equation 6, 14 minus pH is equal to 14 minus pKa plus log salt concentration by base concentration. Now pH is equal to pKa plus log concentration of base divided by salt, where Ka is K is the ionization constant of the conjugate base of the conjugate acid of the base, that is buffers. In the buffer, it is a conjugate acid of the base NH3, and K represent the ionization constant of the equation. NH4 positive plus H2O dissociate into NH3 plus H3O positive. pH is equal to pKa plus log concentration of NH3 divided by concentration of NH4 positive. That is, pH is equal to pKa plus log concentration of base divided by conjugated acid. Buffer capacity or buffer index. It is defined as the number of mole of acid or base required to be added to 1 liter of the buffer solution so as to change its pH by 1 unit. Buffer capacity is equal to number of mole of acid or base added to 1 liter of the buffer divided by change in pH. Dn divided by dpH. Buffer capacity of a buffer is maximum when the concentration of a weak acid and its salt or weak base and its salt are equal, when pH is equal to pK or pOH is equal to pKb. Importance of buffer solution. In biological process, the pH of our body is maintained constant. In spite of various acid and base producing reaction going on our body, in the absence of buffer nature, we could not eat a variety of food and spicy. The buffer action is due to the presence of carbonic acid, bicarbonate ion and carbon dioxide in the blood. Second, in industrial process, the buffer solution is an important part in many industrial process, in electroplating, in manufacture of leather, photographic material dye, in the preservation of food article. in analytic chemistry, in the removal of acid radicals such as phosphate, oxalate, and borate, which interference in the preparation of radical of group 3 of salt analysis. In the complex titrate, matter ion and the ADTA to calibrate the pH meter. In bacteriologist research, culture media are generally buffered to maintain the pH required for the growth of the bacteria being studied. In the determination of degree of hydrolysis, let us first study some term and expression related to salt hydrolysis. Hydrolysis constant. The in general equation for the hydrolysis of salt may be written as Ba plus H2O dissociate into Ha plus BOH. Applying the law of chemical equilibrium, we get concentration of Ha into BOH concentration divided by Ba concentration into H2O concentration is equal to K, equilibrium constant. Since water is present in very large excess in the aqueous solution, its concentration H2O may be regarded as constant, so that we have Ha concentration BOH concentration divided by Ba concentration is equal to K into concentration of H2O is equal to KH, where KH is called the hydrolysis constant. Since Ha concentration and BOH concentration represent the molar concentration of the free acid and free base produced, and Ba concentration represent the molar concentration of the unhydrolyzed salt, the above expression for the hydrolysis constant may be written in a more general way. Kh is equal to free radical acid concentration, free base concentration divided by unhydrolyzed salt. Degree of hydrolysis. The degree of hydrolysis of a salt is defined as the fraction of total salt which is hydrolyzed. For example, if in the sodium of alkaline hydrochloride, 90% of the salt is hydrolyzed into aniline and hydrochloric acid, the degree of hydrolysis is 0.90 or may be expressed as percentage. We are 90%. It is usually represented by the symbol H. H is equal to number of mole of salt hydrolyzed divided by total number of moles of salt taken. Expression for degree of hydrolysis for solution of different type of salt. As salt of strong acid and base do not undergo hydrolysis, therefore to talk of KH or H of salt is meaningless. The case of another three salt is discussed below. Salt of weak acid and strong base represent salt by Ba are usually the hydrolysis may be represented as follow. Ba plus H2O dissociate into BOH plus Ha. B positive plus A negative plus H2O dissociate into B positive OH negative plus Ha. A negative plus H2O will dissociate into OH negative plus Ha is called case of anionic hydrolysis. Suppose the original concentration of salt in a solution is C mol per liter and H is the degree of hydrolysis at this concentration. So we have A negative plus H2O dissociate into OH negative plus Ha. Original concentration is C at initial and 0 at final. Molar concentration is C into 1 minus H and CH. Hydrolysis constant will be given by concentration of OH negative into Ha divided by A negative concentration. So CH square by 1 minus H. If H is very small compared to 1, so we can take 1 minus H is normally equal to 1, so expressed becomes CH square is normally equal to KH. H square is equal to KH by C. H is equal to under root KH by C. H is directly proportional to the 1 by C under the square root. The degree of hydrolysis of salt of weak acid strong base is inversely proportional to the square root of its molar concentration. Second, salt of strong acid and weak base. For example, salt of Ba, the hydrolysis may be represented as Ba plus H2O dissociate into BOH plus Ha. So in this case, relationship is given by H is directly proportional or equal to concentration square root of Kh by C. Third, salt of weak acid and weak base, represented by the salt of Ba, as therefore we have Ba plus H2O will dissociate into BOH plus HA. It involves both anionic hydrolysis as well as cationic hydrolysis. In this case, we have B positive and plus A negative plus H2 dissociate into BOH plus HA. Initial original concentration C0 concentration at equilibrium C1 minus H C1 minus H CH. KH concentration of BOH, HA concentration, B positive concentration, A negative concentration is equal to CH divided by C into 1 minus H into C into 1 minus H is equal to H square divided by 1 minus H ka square. Here the relationship between KH and H does not involve C. Thus, the degree of hydrolysis of such a salt is independent of the concentration of the solution. If H is very small in comparison to 1, we take 1 minus H is equal to 1. So, became it from equation 3, that is KH is equal to H square divided by 1 minus H का square. ठीक है, तो KH is equal to H का square, H is equal to square root of KH. Thank you.